This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai's studies. A link is in the description box below. Does the following series converge or diverge? Well, because I see factorials, I'm going to use the ratio test. And the rules for the ratio test are based on the limit as n approaches infinity of the ratio. So it's a fraction of your sequence, but wherever you see an n, you're going to add a 1 divided by your sequence and then absolute value, because ratio and root tests at Rutgers come with absolute value, and that's going to be equal to a limit, or at Rutgers we say rho. Even though it looks like a p, we pronounce it as rho. And so the rule is if rho is less than 1, rho is greater than 1, rho is equal to 1, then this series converges absolutely, diverges, or it's inconclusive, meaning try another test. So we're going to take the limit as n approaches infinity of our sequence, but wherever we see an n, we're going to add a 1. That's going to be n plus 1 factorial. And then I have 2, but this 2 is being multiplied by the n, and I need to add a 1 to the n. So it's going to become 2 times n plus 1, and then that whole thing is factorial. And so this is this, and then we have to divide by this, or we could just multiply by the reciprocal. So just flip these and multiply by that. In this case, because we know n is equal to 1, so this series cannot be less than 1, so it's always going to be positive. Putting absolute value really makes no difference. So the given series and the corresponding positive series, so it's just the given series with absolute value, is going to be the same thing. But nevertheless, because even though the result is the same, because we used absolute value, we have to use the following rules over here. So this here can be simplified to 2n plus 2, and then 2 plus 1 is 3. And then you always want to switch your denominators, because now similar things are together. To simplify these expressions, you want to ask yourself which is bigger, the numerator or the denominator. Here we have an n, here we have an n, we have n plus 1 in the numerator. So the numerator is bigger, so therefore we're going to leave the denominator alone because it's smaller, and we're going to expand the numerator. What do I mean by expand? I mean take the same thing, and then to expand, to get to the next thing, you just minus 1. So 1 minus 1, that cancels out, we're left with n, so the next thing is going to be n. And I know to stop here because this is what I see here. So to stop, I'm going to say factorial, and then I'm able to cancel it out, and I'm simply just left with n plus 1. To simplify this, which is bigger, numerator or denominator? Well, 2n, but here's a plus 3, here's a plus 1, so the denominator is bigger. So I'm going to leave the smallest thing alone. I'm going to expand the biggest things, so I start with what I have, and then to get to the next thing, I'm minus 1. So 3 minus 1, that's 2, so 2n plus 2. This is not the same thing as this, so I keep going. To get to the next thing, minus 1, so 2 minus 1, that's 1. This is the same thing as this, so I know to stop. So to stop, I'm going to say factorial, and then I can cancel these out, and I'm left with 1 over all this stuff. And because these are being multiplied together, I could just bring this over here. And this is a rational fraction, so we know that we can divide every term in that fraction by the term with the highest power in the denominator. But to see that, it's good to simplify, so you can see it so much more clear. So this becomes 4n squared plus 4n plus 6n plus 6. 6 plus 4 is 10. And now we can easily see that the term with the highest power in the denominator is n squared. So we're going to divide everything by n squared. And so these cancel out to 4. This cancels out to 10 over n. This cancels out to be 1 over n. So this becomes the limit as n approaches infinity of 1 over n plus 1 over n squared. 4 plus 10 over n plus 6 over n squared. You can plug in infinity for n. Infinity squared is still just infinity. Anything divided by infinity when it comes to a limit just goes to 0, because one whole divided into infinitely small pieces becomes so small, it becomes 0. And we know 0 is less than 1. Because rho is less than 1, we know that this series converges absolutely. So let's get to our conclusion. Since, let's just take the limit, is equal to 0, which is less than 1, the ratio test, remember you always have to specify your test, implies that the given series converges absolutely. But again, they didn't ask us if it converged absolutely, they asked us if it converged. So we can use our number 2 tool in our toolbox, the absolute convergence theorem, that says if any series converges absolutely, which we know it does by the ratio test, then that same series converges itself. So we say, and absolute convergence implies convergence by the absolute convergence theorem. This is an important part. You have to cite the absolute convergence theorem. So the given series converges as well. And that is your final answer, that this series converges.